Test for goodness of fit, Chapter 11. In this example, we have a stem plot of 50 birth weights in ounces. So the 4 in row 5 would be a 54-ounce baby. 7 in row 6 would be a 67-ounce baby. We have 2 babies in row 7. I have a 72-ounce baby and a 75-ounce baby, and so forth. So altogether we have 50 birth weights. If we compute the mean and standard deviation, we get a mean of, add up all these birth weights, we get a mean of 105.6 ounces and a standard deviation 19.15 some ounces. And we want to test a couple of hypotheses about this data. With 95% confidence, and that means 1 minus alpha is 0.95, alpha is 0.05. We test H0, birth weights are uniformly distributed from 50 to 149 ounces, versus HA, birth weights are not uniformly distributed. So the first step is going to be to group the data into equal intervals, so there's an average at least 5 birth weights per interval. So I group them by 20s, the 50s and 60s. We had 2 babies in the 50s and 60s, 6 babies in the 70s and 80s, 21 babies 90 to 109, 15 babies 110 to 129 ounces, 6 babies 130 to 149 ounces. So mostly there's only one interval with less than 5 birth weights, and certainly the average is more than 5 birth weights per interval. Step 2 is birth weight is uniformly distributed. Then on the average we expect 50 babies divided by 5 intervals to be 10 babies per interval. So the expected frequency is 10, E equals 10. That's the expected frequency. And then step 3, compute the test statistic. It's each observed minus the expected, square it, divide by the expected. So in the first interval we had 2 babies, 50 to 69 ounces. 2 minus 10 is -8. -8 squared is 64. 64 divided by 10 is 6.4. The next interval, 70 to 89 ounces, we had 6 babies. 6 minus 10 is -4. -4 is 16. -4 is squared is 16. 16 divided by 10, 1.6, and so forth. So we want to add all these up then, and it comes out to be 24.2. And the degrees of freedom are the number of categories minus 1. So we had 5 intervals. 5 minus 1 is 4. So we'll look in row 4, column 0.05 of the chi-square table in the appendix, and that number is 9.488. And because our test statistic is more than the upper critical value that we got from the chi-square table, we reject H0 with 95% confidence and conclude that the birth weights are not uniformly distributed. In fact, they don't really look like they're uniformly distributed. They look like they have a lot of babies between 90 and 119, and then a few babies on either side. They don't look like they're evenly spread out, and they look more like a bell. They might look. It looks like maybe a bell-shaped graph. Let me turn it this sideways here. It looks like they might fit a bell-shaped graph. So that's the next test that we're going to do. We're going to test whether these are normally distributed, which means they would have a bell-shaped graph. So again, 1 minus alpha 0.95, alpha is 0.05. H0, birth weights are normally distributed. HA, birth weights are not normally distributed. And again, we can group the data. We can use the same grouping, but because the normal distribution includes fractions and decimals, and we want to extend these intervals so there's no gaps between the intervals. So we're gonna count everything up to 69.5 ounces as the first interval. So and then 69.5 to 89.5 and so forth, so that we have no gaps between the intervals. Last interval will be over 129.5 ounces, and then we can compute the expected numbers. We have 50 babies, so the expected number of babies in the first interval would be 50 times the probability that x is less than 69.5, and if h0 is true, this is going to we're going to be able to it's going to fit the probabilities that are in the z-table. So we can compute the z-score, subtract the mean, divide by the standard deviation. We get a z-score of negative 1.88, and look in and we can look that up in the table. So it's actually our table doesn't have the negative z-scores, so we'd have to look in positive row 1.88 and subtract it from 0.5 to get a probability of 0.0301, multiplied by 50, and we get 1.505 babies. And then the expected number of babies between 69.5 and 89.5, the z-scores are between negative 1.88 and negative 0.84, and look these up in the table. Again, our table, some books have a separate page for negative z-scores. Our book does not. But in any case, we can look up the positive z-scores in the table, the corresponding positive numbers, and subtract the probabilities to get 8.52 babies. And likewise do the same thing for 89.5 to 109.5, and 109.5 to 129.5, and then above 129.5. So we want the probability that z is greater than 1.25, so it's going to be 0.5 minus the probability that z is less than between 0 and 1.25, and it comes out to be 5.28 babies. And then the next thing we want to do is check that no expected values are less than 1, and that's a yes. And we also want to check that no more than 1 out of every 5 expected values are less than 5, and that's also a yes. Our expected values we had 1 of the 5. We have 5 expected values, and exactly 1 of them were less than 5. So if not, we would have to regroup the intervals so that we have larger expected values. And then we compute the test statistics. Each observed minus the corresponding expected, square it, divide by the expected. So it's we had 2 babies were observed. The expected was 1.505. That was in the 50s and 60s. Square that, divide by the expected, and so forth. And then we come up with a test statistic at 1.267. Our upper critical value is in row 4, column 0.05 of the chi-square table, and because our test statistic is smaller than the upper critical value, we fail to reject H0. Sample does not provide enough evidence to conclude that the birth weights are not normally distributed. And this test can never prove that a variable is normal. It'll either prove with a certain level of confidence that it's not normal, or we don't know. And for this example, we don't know. It might be, and it's possible that the distribution could be very, very close to normal, but not quite exactly normal. And it might take a huge sample to show up that difference. So we never know. We're never going to be able to use this test to say for sure that something is normal. We can only prove that it's not normal. And that concludes this presentation.